Hello, my name is Nemanja and thank you for clicking on my poster. I will be telling you something about modified 7-days adenosine ribonucleotides as antiviral agents. The aim of the project was to prepare the library of 7 modified 7-days adenosine triphosphates and check their inhibitory activities against different viral RNA-dependent RNA polymerases in vitro, and also to check the antiviral effects inside the cell of their parent nucleosides or the monophosphate prodrugs, namely protide and the SATE prodrug. Now, the actual goal of the project was to try to tune the biological properties by varying the size of the substituent on our nucleosides or the triphosphates. So we installed the groups ranging in size from very small methyl group up to the very big naphthyl group. And how did we do that? Well, by organometallic functionalizations on 7-iodo-7-dease adenosine, we were able to obtain the nucleosides, which we then phosphorylated to get the final triphosphates in good to moderate yields. And a similar approach was used for the protide prodrugs. As phosphoramidite moiety was remarkably stable for the coupling conditions, we used either Suzuki or Sonogashira coupling for most of our derivatives to get the final prodrug, or if we were not able to do the coupling on the prodrug, if it required some harsher conditions, then like for the methyl and cyclopropyl group, then I would actually prepare first the modified nucleoside and then react it with this phosphochloridate to obtain the final derivatives. Now, regarding the SATE prodrugs, we used also similar approach in a way. So first we prepared the modified H-phosphonates by Suzuki couplings on the iodinated phosphonates, and this worked in almost quantitative yields. And then we activated the phosphonates with the pivallyl chloride and coupled them with this thioalcohol, and after the acidic deprotection, we got the final derivatives in the moderate yields. And now with this, we proceeded with biological profiling. First, we started with the triphosphates, and what we did is to compare the activities of the triphosphates against the Zika virus polymerase, Japanese encephalitis polymerase, and West Nile virus polymerase, to compare them with remdesivir triphosphate as a standard. And it turned out that the benzofuryl ATP had the best activity of around half a micromole for each 3 polymerases, while there was certain activity also for the thianyl and furyl derivatives, and all 3 were actually quite more active than remdesivir triphosphate. Then we proceeded with the experiments inside the cell. And first I will tell you something about the nucleosides. It turned out that the most active are the smaller modifications, like for example the ethinyl one, or the smaller aromatic modifications like furyl and thianyl one. However, the main issue here was the cytotoxicity, which was the highest for ethinyl, but it also existed for the other derivatives. Heteroaromatic bulkier derivatives of the nucleosides were less active, but also less cytotoxic. Now, regarding the protides, we did not see any basically improvement in activity in regards to, if we compare them with the parent nucleoside. And also what we saw was the selectivity, that our compounds were mostly active against the Zika virus polymerase, but there was certain activity against the SARS-CoV virus as well for the protides and for the nucleosides. And SATE prodrugs, we basically also saw no improvement against the viruses, and their activity was comparable to the protide prodrugs, and the phenyl and benzofuryl SATE were more active than the other ones. Now, to conclude, we have prepared the series of 7 substituted 7-dease adenosine ribonucleotides, and all the NTPs were micromolar inhibitors of different RNA-dependent RNA polymerases, with the benzofuryl one being the most active one. Now, regarding the nucleosides and prodrugs, several of them were found to be submicromolar inhibitors against the different viruses, with the preferences towards the Zika virus. And the smaller aromatic ones, modifications were more active than the bulkier ones, and the nucleosides were more active than the prodrugs. And I didn't show you here how, but we tried to figure out what was going on, and we tried to do metabolic studies and find the active concentration of benzofuryl monophosphate in the cell from the protide or the nucleoside or from the SATE prodrug. And what was quite fascinating, we saw quite a lot of monophosphate from the SATE prodrug, and yet we saw no biological activity, which means that it could be either that the second phosphorylation is the issue, or maybe there's some efflux from the cell, or maybe our nucleosides have alternative mode of action, which we do not know yet, and this is a question that needs to be addressed. So thank you for your attention, and I would also like to thank my supervisor, Professor Michal Hocek, and the variety of our collaborators which were doing the biological activity for us. Thank you once again, and do not hesitate to contact me for any questions. Thank you.